Hello, and welcome to Lecture 3 of Electromagnetic Induction in Phys 1204. Last lecture we saw Lenz's law, which tells us when we will see an induced current in a coil and which direction it will flow. This lecture we'll see Faraday's law, which is going to let us figure out how big the induced current will be. 2 lectures ago, we saw that by moving a conducting rod through a magnetic field, we produced an EMF in that rod that we called a motional EMF. And with a clever setup, we could make that drive a current. And let me remind you that we call it an EMF because there's an E field here pointing from positive to negative, but there's a magnetic force pushing charge against the E field so that it flows from low potential to high potential. Well, that's what we mean by an EMF. It's the work per unit charge being done by some force that's making current go against an E field. Well, in fact, we saw the same thing in the coil in the wire, in the coil with the magnet moving in and out. And let's think about that. There was a resistor up here, and we were actually measuring the voltage across the resistor. But the only thing in the circuit was the resistor and the coil. So Kirchhoff's loop law tells us that the voltage drop across the resistor must have been equal to a voltage rise across the coil. And so whichever way the current was going, it must have gone through a voltage drop in the resistor, a rise in the coil, and so the potential versus position graph would look like this. All I'm getting at here is that the current is going from low potential to high potential in the coil. And so there is a force there which is pushing it against an E field. And so that means that's an EMF. The idea that there's an EMF in the coil is what's going to allow us to understand Faraday's law, because it's all about this EMF. So remember Lenz's law. An induced current flows whenever the magnetic flux through the coil changes. And Lenz's law tells us which way. It tells us that the induced B field due to that induced current opposes the change in the flux. But note, this only tells us when current flows and which way. It doesn't allow us in any way to figure out how big that current should be. So that's where Faraday's law comes in. It's going to allow us to predict the size of the current, but it's going to do it by telling us the size of the EMF that will drive the current. And Faraday's law is sort of very simple. It says that that EMF is just equal to the rate of change of the magnetic flux through the coil. Now, I just want to point out there's no proportionality constant out here. And it might not be obvious that the units of this are even correct. We'll check that in a moment. But the fact that there's no proportionality constant out here has to do with the fact that our magnetic field units are intimately connected with the units we use for current. And if we had decided to choose our units differently, or indeed in another commonly used set of units called Gaussian units, we would need a constant out here in front. But for us working in SI units, it's nice and convenient, and it's just that the EMF is the time rate of change of the magnetic flux through the coil. So let's just have a quick look at those units. And in fact, we've already seen it sort of a few lectures ago. So epsilon, that's an EMF, it's in volts. And this is a flux, so a flux we already saw was a Weber, although note that that is a Tesla meter squared. And that's a time derivative, so that's per second. But I already showed a couple of lectures ago that a Weber is also a volt second. And so this does work out. This is in volts. Let's use this to calculate something now. So here's a setup. And I'd better explain this carefully because it may not be clear what's happening here. Here is a coil. And we've got a current running in the coil. So there's a supply wire, and current is coming in here, and it's running around clockwise in the coil and then back out here. And the coil has a 5 centimeter radius, and we will at some point want to know the B field inside, so I'm reminding us what the formula is. That's strictly speaking just the B field in the very middle. And there are 100 turns in this coil. Now in the middle of the coil there's a copper ring, a fairly small copper ring. And so if you think about what happens, if we change this current, that will change the B field in here, which will change the flux inside the copper ring. And so as soon as we change the flux in the copper ring, we will drive a current around the copper ring. So that's what we're going to figure out. We're going to figure out which way that current goes and how big it is. So I've done some calculations ahead on the copper ring because they're not the main event. I'll just quickly summarize them here. The copper ring is about the size of a ring you might wear on your finger. It's about 0.64 centimeters in radius, so that gives us a circumference and an area, and also we're going to need to know its resistance. So I said if you slice it, then the cross section that you slice ends up having this area, and we can calculate its resistance. And I'm not going to go through that because it's not the main event. You can look at it if you want. What we're now going to do is change this current. So let's say that initially we have 5 amps running in the coil, and we turn it off so it comes to a screeching halt. Now it won't come to a stop instantly, so let's say it takes half of a millisecond to drop from 5 amps to nothing. So there is our graph of current versus time in the coil, and we want to know what happens inside the ring. So first let's work out the direction. So our coil is the source of a B field, and the right-hand rule tells you that that B field is into the page. So there is our B due to the coil. When the current stops, that B field will rapidly disappear, and so that is a change, a delta B, which is out of the page. Well, Lenz's law tells us then that there will be an induced B field produced by the induced current in the ring, which is into the page, and right-hand rule tells you that our current in the ring is going to be clockwise. That's the direction for this induced B field. Okay, so now we know the direction. I've already apparently called clockwise positive at the moment, so we'll just keep working with that. We will eventually graph the current in the ring versus time. Let's now figure out how big it is, and we're going to use Faraday's law. So here it is. And note that it has absolute values. Now you can, in fact, carefully work through sign conventions and not use absolute values. It ends up just being epsilon equals negative d phi m by dt. But most of the time you're better off using Lenz's law to figure out your directions, and only use Faraday's law for the magnitude, like so. So that will be our EMF in the ring due to the change in the B field caused by changing the current in the coil is going to be d by dt, and I'm going to drop all signs and absolute values here. I already know the direction, so let's just work in magnitudes. So d by dt of a flux, and so that is a BA, right? Because this B field is perpendicular to this surface inside the ring, so there's no cosine of an angle. And this ring is pretty small, so it should just be getting that roughly constant B field in the middle of the coil, which should have this magnitude. A is a constant, that is just the area of the ring, which I've calculated here. And so I can pull that out front, and I have d by dt of B. And B is n mu naught I over 2r. Well, that's all constants except for the I, the current. So I have And I've made a nice linear I versus t, so I can just take that slope. It's going to be a delta I over a delta t, and I don't care about sign, over delta t, which I can just read off of the graph. So I am now going to plug in the numbers and get this EMF, and you might want to do it at the same time in your own calculator. I get 1.6 times 10 to the negative 3, and let's look at the units. Meters squared, well, one of those meters squared takes out that meter. Amps take out amps, and so at the moment we're left with Tesla meters squared per second. But a Tesla meter squared is a Weber. So we've got Webers per second, and we've already seen that a Weber is a volt second. So this is coming out in volts, as we expected it had to. And so we've got 1.6 millivolts. Now that's not too impressive, except that the resistance of this ring is only 1.7 times 10 to the negative 4 ohms. So if you work out the current in this ring, it's that epsilon over the resistance, and that's roughly 10 amps, which is a pretty big current. Let's just quickly graph that, because I find students often forget when current is induced. So we've already discussed I set clockwise as positive, and our current in the coil was like so, and we want the current in the ring, and we know it came out to 10 amps, and it's also clockwise. But remember, there is no current in the ring when the current in the coil is constant. This 10 amps only flows in the coil for this half of a millisecond here, while the current in the coil is coming to a rapid stop. We've seen a lot of things in your physics courses that perhaps were counterintuitive, but, you know, most of it, once you got used to it, I hope, has made a fair bit of sense. But here is something that we're about to see that's actually kind of weird. And I will say, we can explain it, although not really with what we're going to learn in this course. So let's think about a sort of a funny situation. Let's set up a wire loop, and somehow we can make a B field that's just in this middle area. So in this shaded region, there's a B field. And I'll say, this is difficult to do experimentally, but you can do it. There are ways you can make a B field like this. And I'll say it's into the page and it's increasing. If you work through all of Lenz's law and so on, you will find that if this B field into the page is increasing, it induces a current around this way in the wire loop. Okay, except think about that. That B field is only in here. B is 0 out here at where the loop is, which is where the electrons are. How the heck do the electrons know that the B field in here is increasing so that they know that they should flow? We've got something spooky happening where by changing the B field here, we're able to have sort of an action at a distance on the electrons in the loop. Well, in fact, we aren't, but it's going to take a little bit of explanation to see what's actually going on here. The explanation is that a changing B field induces an E field, but it's an E field unlike any E field we've ever seen because it goes around in circles like so. And that has all kinds of implications which we don't have time for. All I have time to say is that if you have an E field that's changing, then it also induces a B field. And now this can go back and forth. A B field induces an E field, which induces a B field, which induces an E field, and that means this can travel through space. And that's what light is.